Welcome to G Fun Facts Online, where we strip away the noise and dive straight into the science that is reshaping our world. Today, we are exploring a technology that literally allows us to see the invisible. We are talking about upconversion nanoparticles, or UCNPs. To understand why these materials are considered photonic alchemists, we first need to look at how light normally behaves. There is a fundamental rule in physics known as the Stokes shift. Named after Sir George Gabriel Stokes, this law dictates that when a material absorbs light, it emits light of a longer wavelength, meaning lower energy. Think of it like dropping a ball. It bounces back up, but never quite as high as where it started. You lose some energy to heat or vibration. This is how standard fluorescent dyes work. They absorb high-energy ultraviolet or blue light and emit lower-energy green or red light. Upconversion nanoparticles, however, seem to break this rule. They exhibit what is called an anti-Stokes shift. They take in low-energy infrared light, the kind used in your TV remote that passes harmlessly through your hand, and they combine that energy to spit out high-energy visible light, like brilliant blues and greens. They essentially perform a mathematical magic trick where 1 + 1 = 2. They absorb 2 or more weak photons and sum them up to emit 1 strong photon. The secret to this trick lies in the materials used, specifically the lanthanides, or rare earth elements. Unlike organic dyes, which have messy, broad energy levels, lanthanides like ytterbium, erbium, and thulium have very sharp, ladder-like energy structures. The most efficient way they work is through a process called energy transfer upconversion. Imagine a ladder. We dope the crystal with a sensitizer, usually ytterbium. Ytterbium acts like an antenna. It loves to catch near-infrared light at 980 nanometers. When it catches a photon, it gets excited, but instead of letting that energy go, it holds it and passes it to a neighbor, an activator ion like erbium. That transfer pushes erbium up one rung on the energy ladder. Then, a second ytterbium atom catches another photon and passes that energy to the same erbium atom, pushing it up to a second rung. Now highly energized, the erbium relaxes back down, releasing all that stored energy at once as a single photon of visible light. This is the physics of the impossible made possible. Recently, in 2024 and 2025, scientists even unlocked a phenomenon called room temperature superfluorescence in these particles. This is a quantum state where all the ions synchronize their emission, firing a superpulse of light millions of times brighter than normal, a behavior previously thought to only happen near absolute zero. But knowing the physics is only half the battle. Synthesizing these particles is a delicate art of chemical engineering. The goal is to build a perfect crystal host. The gold standard material for this is sodium yttrium fluoride in a hexagonal crystal phase. We use fluoride because it has low phonon energy. In simple terms, the crystal lattice is very quiet. It does not vibrate much. If we used a material that vibrated a lot, like an oxide, those vibrations would steal the energy from the ions before they could emit light. Making these crystals involves a process called thermal decomposition. We mix rare earth chlorides with oleic acid and cook them at 300 degrees Celsius in an oxygen-free environment. The oleic acid acts as a surfactant, controlling the growth so the particles do not clump together. One of the most critical advances in this field is core shell engineering. You see, a naked nanoparticle has a major weakness. The ions on the surface are exposed to the solvent, which kills their energy. To fix this, scientists build an onion-like structure. They grow an active core containing the glowing ions, and then wrap it in an inert shell of undoped material. This shell acts as a shield, protecting the core from the outside world and significantly boosting brightness. Sometimes, we even use an active shell to harvest different wavelengths of light, creating a complex energy migration path within a single tiny particle. Once we have these particles, the applications are mind-bending, particularly in bioimaging. This is the killer app for UCNPs. Traditional microscopy uses blue or UV light, which has two problems. First, it does not penetrate tissue well. Second, biological tissue naturally glows green when hit with UV light, creating a noisy background. UCNPs solve both. They are excited by infrared light, which falls into the biological optical window. This light passes through tissue easily, allowing us to see centimeters deep rather than millimeters. Furthermore, tissue does not upconvert. When you shine infrared light on a body, the background remains pitch black. Only the nanoparticles light up. This provides infinite contrast, allowing us to spot even a single cancer cell deep inside an organ. We can also tune the colors. By changing the dopants, we can have blue, green, or red particles, allowing for multiplexed imaging where we track different biological targets simultaneously. Beyond just seeing, these particles can heal. In photodynamic therapy, or PDT, doctors use a drug that turns toxic to cancer cells when exposed to light. The problem is getting light deep into a tumor. With UCNPs, we can attach the drug to the particle. We shine harmless infrared light through the body. The particle converts it to UV light right inside the tumor, and that activates the drug, killing the cancer from the inside out. Even more futuristic is the field of optogenetics. This involves controlling brain cells with light. Typically, this requires implanting fiber optic cables into the skull. But with UCNPs, researchers have developed transcranial optogenetics. They inject the particles into the brain and shine an infrared laser on the outside of the skull. The light goes through the bone, hits the particles, and turns into blue light, triggering the neurons. This has been used to stimulate memory and stop seizures in mice without a single wire entering the brain. The utility of UCNPs extends to energy as well. Our current silicon solar panels are blind to infrared light, which makes up about 44% of solar energy. By placing a layer of UCNPs behind a solar cell, we can catch those lost infrared photons, upconvert them to visible light, and bounce them back into the cell to create electricity. Recent work with perovskite solar cells has shown that adding neodymium-doped UCNPs can boost efficiency significantly, pushing power conversion past the 21% mark while improving stability. In the world of security, these particles are guardians against counterfeiting. We can create particles with a unique spectral fingerprint, a specific barcode of colors that is impossible to fake without the exact chemical recipe. Some advanced UCNPs even change color based on the power of the laser you shine on them. A security stamp might look red under a low-power light, but turn green under a high-power scanner. This dynamic color shifting is extremely difficult for counterfeiters to replicate. Finally, these tiny crystals are finding a home in the future of computing. Neuromorphic computing aims to build chips that mimic the human brain. Researchers are using UCNPs to create optical synapses. When infrared light hits the particle, it converts to visible light, which then generates an electrical signal in a transistor. Because the upconversion process has a slight time delay, it mimics the memory and plasticity of a biological synapse. This is paving the way for optical computers that can learn and recognize patterns just like we do. Of course, challenges remain. The biggest hurdle is efficiency, or quantum yield. Most of the energy is still lost. Scientists are combating this by attaching organic dye antennas to the surface of the particles to catch more light, or by using plasmonic enhancement with gold nanoparticles. There are also questions about the long-term toxicity of lanthanides in the body, although silica and polymer coatings have shown great promise in making them biocompatible. We are also moving towards using 808 nanometer light instead of 980, as it causes less heating in water and tissue. Upconversion nanoparticles represent a triumph of materials science. They allow us to bend the rules of light to our will, peering through skin without cutting, securing our currency, and harvesting lost energy. As we master the challenges of brightness and synthesis, these tiny crystals will essentially become the invisible engines, powering a very visible future in medicine and technology. That wraps up our deep dive into the world of UCNPs. Thanks for listening to G Fun Facts Online.